Recurrent neural networks, or RNNs, are a class of neural networks designed for processing sequential data. Unlike traditional feed-forward networks, RNNs possess an internal memory that allows them to retain information from previous inputs in a sequence. This characteristic makes them uniquely suited for tasks where the order of data points is crucial. Consider data types such as natural language sentences, time series measurements, or video frames. In these cases, each element's meaning or value is often dependent on preceding elements. RNNs address this dependency by feeding the output of a hidden layer back into itself as an input for the next step. This recurrent connection enables the network to learn patterns and dependencies across time steps. The same set of weights is applied at each step, allowing the model to generalize across different sequence lengths. This shared parameterization is a key efficiency of RNN architectures. Despite their theoretical elegance, vanilla RNNs face significant practical challenges, primarily the vanishing and exploding gradient problems. During backpropagation through time, gradients can either shrink exponentially or grow uncontrollably. This occurs as the error signal is propagated backward through many time steps. Vanishing gradients make it difficult for the network to learn long-term dependencies. Information from earlier steps effectively gets forgotten by the time it reaches later steps. The weights connecting to earlier time steps receive very small updates, hindering effective learning. Conversely, exploding gradients lead to unstable training and large weight updates. This can cause the model to diverge or produce NaN values. Gradient clipping is a common technique to mitigate exploding gradients, but it does not solve the vanishing gradient problem. These gradient issues severely limit the ability of simple RNNs to model sequences with long-range dependencies. This limitation spurred the development of more sophisticated recurrent architectures. To overcome the vanishing gradient problem, long short-term memory networks, or LSTMs, were introduced. LSTMs are a special kind of RNN capable of learning long-term dependencies. They achieve this through a sophisticated internal structure called a memory cell. Each LSTM unit contains three primary gates: the input gate, the forget gate, and the output gate. These gates are sigmoid neural network layers and a pointwise multiplication operation. They regulate the flow of information into and out of the cell state. The forget gate decides what information to discard from the cell state. The input gate determines what new information to store in the cell state. Finally, the output gate controls what part of the cell state is outputted to the next hidden state. This gating mechanism allows LSTMs to selectively remember or forget information over extended periods. This enables them to capture dependencies spanning hundreds or even thousands of time steps, making them highly effective for complex sequence modeling tasks. Gated recurrent units, or GRUs, are a slightly simpler variant of LSTMs. They were introduced to reduce computational complexity while retaining much of the LSTM's ability to handle long-term dependencies. GRUs combine the forget and input gates into a single update gate. A GRU unit has two main gates, the update gate and the reset gate. The update gate determines how much of the previous hidden state should be carried over to the current hidden state. It essentially controls the balance between remembering past information and incorporating new input. The reset gate decides how much of the previous hidden state to forget. If the reset gate is close to 0, the hidden state is effectively reset, allowing the model to discard irrelevant past information. This helps in learning dependencies over varying lengths. While GRUs have fewer parameters than LSTMs, they often perform comparably on many tasks. Their simpler structure makes them faster to train and less prone to overfitting in some scenarios. The choice between LSTMs and GRUs often depends on the specific application and dataset. RNNs, particularly LSTMs and GRUs, have revolutionized natural language processing. Their ability to process sequential data makes them ideal for understanding and generating human language. One prominent application is machine translation. In machine translation, an encoder RNN processes the source language sentence, compressing its meaning into a context vector. A decoder RNN then uses this context vector to generate the target language sentence word by word. This sequence-to-sequence architecture is highly effective. Another key application is sentiment analysis. RNNs can analyze sequences of words to determine the overall sentiment expressed in a text, classifying it as positive, negative, or neutral. This is crucial for understanding customer feedback or social media trends. Text generation is also a powerful application. Given a starting sequence, an RNN can predict the next most probable word, generating coherent and contextually relevant text. This is used in chatbots, content creation, and predictive text features. Beyond NLP, RNNs are extensively used in time series forecasting. Time series data, by its very nature, is sequential. With future values often dependent on past observations, RNNs excel at capturing these temporal dependencies. For instance, in financial forecasting, RNNs can predict stock prices or market trends based on historical data. They can identify complex patterns that traditional statistical models might miss, such as nonlinear relationships and long-term dependencies. In weather forecasting, RNNs can predict future temperature, humidity, or precipitation based on past meteorological readings. This helps in disaster preparedness and agricultural planning. The sequential nature of weather patterns aligns perfectly with RNN capabilities. Energy consumption prediction is another vital application. RNNs can forecast electricity demand based on historical usage, time of day, and external factors. This enables more efficient energy grid management and resource allocation. Recurrent neural networks, with their inherent ability to process sequential data, represent a fundamental advancement in deep learning. While vanilla RNNs struggle with vanishing gradients, architectures like LSTMs and GRUs effectively mitigate these issues. These advanced RNN variants have enabled breakthroughs across diverse fields, from understanding the nuances of human language to predicting complex time series patterns. Their capacity to learn and remember long-term dependencies makes them indispensable tools for data scientists. As data continues to grow in complexity and sequential nature, RNNs and their evolving architectures will remain at the forefront of artificial intelligence research and application. Their impact on how we analyze and interact with sequential information is profound and continues to expand.